Big O notation is a little bit like the sculptures of the Romanian-born French artist Constantin Brancusi, in that it does away with all details and only keeps the essence. If you have ever studied Big O notation before, you have most likely been presented with little more than sleep-inducing formal definitions like this one, with little attention paid to why and how we use it for expressing algorithm efficiency. In this tutorial, I will take another approach altogether. I will first explain graphically what exactly the worst case, best case, and average case time complexity of algorithms is. And then we will discover together how Big O notation helps with analyzing their asymptotic efficiency. A simple method for understanding the efficiency of an algorithm is the experimental one. We time the execution on several test inputs, as we are doing here with the sorting algorithm. The goal is to understand how to predict the running time of the algorithm as a function of the input data, but without actually running the algorithm itself. Typical algorithms tend to take less time for smaller inputs and more time for larger inputs. Therefore, we first conceptually group all possible inputs into equivalence classes, based on the size of the input. There is one equivalence class for every input size. Each contains all inputs of a given size, and it is worth keeping in mind that there might be an infinite number of such inputs. Let us concentrate on an arbitrary class of inputs. We conceptually run the algorithm on each input in the class. And we write down the corresponding execution times. We look for the slowest time and mark the corresponding input in red. If necessary, we break ties arbitrarily. We mark the input with the fastest time in green. We conceptually compute the running times for all inputs. We identify the slowest time in each equivalence class. And we mark the corresponding inputs in red. We identify the fastest time in each equivalence class. And we mark the corresponding inputs in green. The series of inputs marked in red is called the worst-case scenario of the algorithm. To obtain the worst-case time complexity of the algorithm, we simply plot the running time for each input in the worst-case scenario against the input size. The worst-case time complexity is therefore a function, typically strictly increasing, that maps the size of the input into the time required by the algorithm to finish on inputs of that size. Going back to the equivalence classes, the series of green inputs is the best-case scenario. The best-case time complexity is obtained from the best-case scenario by plotting the running times as before. Let us go back to the equivalence classes once more. Sometimes we know how likely each input in a given equivalence class is. Skipping some details, it makes sense in this case to compute the average running times over all inputs in each equivalence class. The plot we obtain using these averages is called the average case time complexity. The average case time complexity can sit anywhere between the best case and the worst case time complexity, and it is also typically strictly increasing. So far, we have expressed the running time in nanoseconds, but this is not the right way. So far we have measured running times on our low-end laptop. If we make the same measurement on a pricier machine, we could get wildly different results. This is an issue, because we want our algorithm analysis not to depend on any particular technology. Moreover, we want our analysis to survive well into the future, with faster computers still. So how do we measure time if not in seconds, or nanoseconds? The key insight is to take a closer look at the individual computation steps of the algorithm, such as assignments or increments. Simplifying things a little bit, single computation steps take a constant amount of time to execute. An assignment could take 0.1 nanoseconds on a low-end machine, or 0.01 nanoseconds on a pricier one. We call it a constant amount of time because, crucially, it does not depend on the input data or its size. So instead of timing our algorithm on a particular computer, we will count the number of computation steps the algorithm performs. This count is the same on any computer. To obtain the actual running times, we multiply this number by the amount of time it takes each machine to execute one step. These amounts are sometimes called the machine constants. Now we redo all previous work of grouping inputs by size. This time we conceptually determine the number of computation steps the algorithm performs on each input. We find the worst-case scenario and the best-case scenario as explained earlier. We plot the worst-case time complexity and the best-case time complexity. By averaging the number of computation steps in each equivalence class, we can also compute and plot the average case time complexity. The three types of time complexity are now expressed in a more abstract manner, using computation steps on the y-axis instead of nanoseconds. Our analysis is now independent of any particular technology used to run an implementation of the algorithm. Plotting the time complexity of an algorithm is surely useful, but we can do even better. Typically, the discrete points of the time complexity roughly follow the graph of some function of the input size. A quadratic function happens to fit the plot for our worst case scenario, and a linear function fits the plot for the best case scenario. Let's forget about the average case for now. Finding expressions that predict the running time as a function of the input size is the goal of analyzing the efficiency of algorithms. But finding these exact expressions can be problematic, for a few reasons. As you can imagine, the exact values of the coefficients can be difficult or even next to impossible to find in practice for all but the simplest algorithms. Then, depending on the algorithm, there might not even exist a nice closed-form expression that fits the graph. But more importantly, the exact coefficients depend too much on the low-level details of computation steps. I could count an assignment as a single atomic computation step. Someone else could consider that there is one step for loading y, another step for storing its value into x, and therefore count 2 steps for this assignment. Both of these views are equally valid. Depending on what exactly constitutes a computation step, we could end up with slightly different plots. Skipping some details, the intuition behind notations such as big O, theta, and omega, is that all such slightly different functions, which still have the same growth factor, should be considered equivalent. In our example, the functions in the red region would be denoted by theta of n squared, and it will contain roughly all functions whose dominant term is n squared. For the best case time complexity, the green region would be denoted by theta of n, and it will contain roughly all functions whose dominant term is n. Let's start by defining theta. Theta of some function g is a class of functions, intuitively containing all functions roughly in the same region as g. When is a function, which we call f, part of theta of g? First of all of our notations are about asymptotic complexity. Asymptotic is a fancy word meaning that we are not interested in how the function performs for small values of n. Instead, we are interested in how the functions behave as n gets larger and larger, growing towards infinity. In order to account for the meaning of asymptotic, we first choose a convenient constant, called n0. We forget about everything to the left of n0. We choose conveniently two real-valued positive constants c1 and c2. We plot the graph of c1 times g of n and c2 times g of n. Any function whose graph is in the shaded region is part of theta of g. Functions outside the shaded area for any choice of constants are not in theta of g. Now that theta is defined, big O and omega are both very easy. For big O notation, there is no constant c2. Graphically, this means that big O notation only defines an upper bound, the lower bound being the horizontal axis. This means that all functions in theta of g are also in big O of g. But there are functions in big O of g that are not in theta of g. Omega notation is dual to big O notation. For omega notation, there is no constant c1. Graphically, omega notation only defines a lower bound. The shaded region has no upper bound. This means that all functions in theta of g are also in omega of g. But there are functions in omega of g that are not in theta of g. In fact, it is easy to see graphically that theta of g is the intersection of big O of g and omega of g. One common misconception in algorithm analysis, caused probably by the fact that big O notation is about upper bounds, is that big O notation is only about the worst case time complexity. In fact, we can analyze any of the three scenarios using any of the three notations. It is not practical, nor possible in general, to run the algorithm on every single input in each equivalence class in order to find the worst case, best case, and average case time complexity. Instead, we follow a more analytical approach based on analyzing the source code. If you would like to learn more on this, watch my tutorial on bubble sort, which is in fact the mystery algorithm with the best case time complexity of theta of n and the worst case time complexity of theta of n squared that I've been using throughout this tutorial. For the analysis of a more advanced algorithm involving recursion, watch my tutorial on merge sort. If you are interested in the average case time complexity, watch my tutorial on quick select. Find the links to these tutorial in the description box below the video. There are many more things that I could have covered in this tutorial, but it is long enough as it is. But I do plan a follow-up tutorial covering some of these issues. So make sure you subscribe to the Truly Understanding Algorithms YouTube channel. Hit the bell icon to get notified of any future uploads.